Hello again, everybody. Now I know this is the last presentation. I'll try to end with practical hands-on application. It's about visualizing 3D movements using IMU Fusion on NuttX. So real quick introduction, I'm gonna mention what Sensor Fusion is, the Fusion library, what is MQTT, and we're gonna do a live demo on 3D visualization. So a real quick introduction, if you've never used an accelerometer before, it's just a device that measures its own acceleration. So if you leave an accelerometer on the table, it's gonna read negative 1G, or 1G, depends on your reference, right? So it's gonna read only the Earth's gravitational field. So that's what an accelerometer does, quite simple. The gyroscope is a little bit trickier. It measures angular velocity. So let's say we spin it real fast, it's gonna give you a reading that's in degrees per second. However, accelerometers also have drift, which is hard to compensate. There's also a magnetometer, which is a device that measures the magnetic field. Basically, it tells you where north is, the magnetic north. And if you know where north is, you know where the rest is. All those are readily available, they are cheap, and it has driver support on NuttX. It's a real plug and play. Then, when you talk about those sensors, you have Sensor Fusion. What Fusion does, it's knowing that each sensor has advantages, disadvantages, weak points, strong points. What you do with Sensor Fusion is you get a lot of sensors together, and we extract the information that we need with more accuracy, with precision. Obviously, nothing's perfect. But in this example, I'm using an accelerometer and a gyroscope. So it's a two-sensor fusion, let's say. In my case, I'm going to be retrieving Euler angles, which is your pitch and roll. So it's a way of measuring. It's quite complicated. I think I have a figure here. Yes, so you have yaw on the vertical axis, roll on the longitudinal axis, and pitch on the lateral axis. So your pitch and roll is going to give us the angles that we are changing in reference to this axis. It has lots of applications. I think there's another figure. Okay, that's later. There's autonomous vehicles depend on those sensors. Wearables, so how your bracelet knows you are running or walking. It's all about sensor fusion. Orientation for robots, it's definitely dependent on accelerometers and gyroscope. It needs to know how to stand and how to what its position is at the moment. You can also do sensor fusion with things like radar, LiDAR, GPS, whatever sensor is giving you feedbacks on the real world. You can put those things together and fusion it somehow for your application. It's quite complicated mathematics to implement. It's not something that you do in a few lines of code. You really need a mathematical background. However, lucky for us, some people have done that before. We just get the easy part, which is to use it. Then this guy, Medwick, he had his PhD, and he developed a fusion algorithm, which is called the attitude and heading reference system. The good thing about it, I mean, it's a good job, good work he did, obviously, but he did something different, is that his source code is available online. And it offers great accuracy. It's perfect, simple to use, it works fine. And usually those things are closed, right? I mean, if you develop a drone, you're gonna let your stabilization code totally close. But this work is available on GitHub, and this company, I think they are maintaining the code now, I'm not sure, but it's available to use, it's free for use. It's simply customizable, configurable. You can use magnetometer, accelerometer, and gyroscope, or you can use just accelerometer and gyroscope. You're gonna lose a bit of precision, which is what I'm doing here, but it still works. It's implemented in C++, so you need to take that in consideration. A real quick example of what you can do with that. So you can, he has a wireless little box, so you can keep, there's no audio, but can they see?
Should have an audio?
No, it shouldn't. There's no audio. It's just the video. But people can see the video, right?
Yes.
Okay.
No, but he
Wait a minute.
No, people can see.
Okay. So that's what I'm trying to do today. That code actually is on my GitHub, the code to do this. So MQTT, I mentioned MQTT because in this example, I'm trying to transmit the data that I process using the Fusion library, use MQTT to my computer so it can see the movement in real time. So MQTT is a messaging protocol. It's very widely used in IoT. Quite simple. You need let's say your PC is the broker. So you bring up MQTT like a server on your PC, and it's gonna monitor whoever is publishing or subscribing to your broker. So let's say I have an Arduino that reads temperature and pressure. I can read temperature and send to the temperature topic, which is like, it's like your group on WhatsApp, and you can send the temperature to this topic, and whoever is subscribed to this topic can read the message. It's very straightforward. However, you need a middleman. In NuttX, we have MQTT examples, and we have the MQTT implementation available, real plug and play, quite simple. So the proposal here is we have the IMU driver. So we read acceleration gyroscope data. Then we have MQTT for communication. And we have 3 tasks. We spin up a IMU read task. This time is just 10 times a second. It's quite slower. This task will give the measurements to the sensor ops task that's going to process the data, retrieve the Euler angles that the Fusion library generates, and then an offload task that's just isolated to organize this data and send it through MQTT. In this case, I'm using a ESP32 and the MPU 6050. Okay, let's a little bit about the Fusion implementation. I'm not sure you guys can see this, but to start the Fusion library, it's very straightforward. Just Fusion initialize. And once you have that, we receive from a queue the accelerometer data and increment a counter. Then we calculate the Z and YX from the raw data to a value in G. You can see that Z here is actually reading for X because I mounted it wrong and I corrected here. Then we also convert ZYX axis. ZYX gyro axis. And we tell Fusion to create a Fusion vector with the gyroscope data and then an accelerometer vector with the acceleration data. And we update the Fusion instance. So I pass the Fusion, I say Fusion update with gyroscope, accelerometer, and my sample period. It's important that your sample period is accurate. And once it's updated, I can extract this value and convert to the Euler angles. So this should give me back a yaw, pitch, and roll data. Once that's done, I can just send those values through a queue to offload them. And While I'm offloading, I receive this data, and sorry, that's one missing. I put the entire data on a screen, your pitch and roll, on a string, sorry. And then finally, I do an MQTT publish. That's it. The data should be sent. Really straightforward. That's nothing much much else that we have to do. So on NuttX, this code is available on that link. There are instructions that you have to create symbolic link to add this implementation to the NuttX app folder. And there you just configure the sensitivity of the accelerometer, the sample rate, which is 10 Hertz here. The most important part here is the broker address, the IP address. So NuttX can connect to the broker, which is going to be running on my notebook. And also we have to enable MQTT and, in my case, Wi-Fi. Now, the idea that what I'm going to be showing here is based on this implementation that's available on this link. This is based on, it's a Python application that's based on Pygame, PyOpenGL, and PySerial. I modified it so it could read from MQTT instead of the serial port. And what it does is it creates a 3D object, and it's going to rotate this object based on your pitch and roll data that I tell it to. So it's quite simple. I just need my virtual environment, install the requirements. I have a simple MQTT script that I'm going to run. It's going to dump all the data, and then we can see it live. I want to try it live. Chances of it not working are high, but we are going to try it anyway. So I have the MPU mounted on this little box. It has an external battery, which is not working. So I had to do a small gambiarra and put a power bank on it, but it should be fine.
What is a gambiarra?
A gambiarra?
Can you explain for
What is a gambiarra? What? It can be a trick, like a cheap trick, yeah. Any kind of trick that's cheap. It often doesn't look good, like this tape. I would have to research a lot. Okay, so you can see, no? Right? Okay. Okay. So first thing I'm gonna have to do is I'm on my the font size. Okay. Yes. Let's. Isso foi? Acho que dá para ver, né? Ficou um pouquinho maior. Okay. So I'm on the correct Wi-Fi. I'm going to power on my little gambiarra. It's upside down. Ready. Okay, it's powered on. So what do I do now? Okay. I have please work. Yeah, it works. So I'm connecting to the Nutshell using a telnet server. I'm in, okay, it's good. On my computer, I'm going to start it's small again. I'm starting the MQTT broker. It's monitoring on port 5000. So anyone who connects on that port is going to have a broker available. Now I have a simple script here that does a dump. Essentially, it reads the port and dumps everything that comes in text. So we can see if it's working before I actually try to show this thing. So it's connected, okay. Now I can just call my application, which is Fusion Dem. Okay, data offload starts. Okay, it's all right, something's coming. A bit slow, but that's okay. I'm using my phone as a router. I don't have access to the Wi-Fi here for this thing. So we can now, let's see, view. Okay, I think we're good. So If I turn it like that, it stopped. No, it didn't. No, it's the internet. It's working here. So it just takes a while to update. Yeah, the connection is a little bit. I'm gonna try something else. Let me bring my router close. You can pass it on, please.
I will use the camera and try to focus you.
Maybe you can have a faster feedback using this screen here. You have a better feedback, right? Oh, wait, the router. So you can see that it's actually a simple implementation, but it can be useful. I mean, you can like Alan gave me this idea a few times, so credit to Alan. He said something about a toy and some arms so we could move it.
Like
yeah, it should be nice to put in some like trunk or other or cars and other equipment, heavy machines that can move. For example, robot army.
Yeah.
And so people can visualize in real time what's happening. So it is mostly used, useful, for example, in digital twin applications. Yeah, so this is really cool demonstration. And yeah, I think once again,
I'm glad it worked.
yeah.
I was quite afraid because I didn't have the Wi-Fi. Maybe my phone wouldn't accept it, but it's working.
We already realize it's working
can
fine.
you show to the camera?
Yes.
Yeah, maybe.
Yeah, here. You can show them. You haven't played with it.
Okay. I will.
Try to get some feedback here.
Try to see your hand where you need to focus here. I mean, no.
More near?
See your image. Try to
Here.
see your image.
Oh, okay. Right. Just, I cannot see anything too small. Okay. Okay, now I can see. Because I am looking in the front of the camera, but the camera is side.
Here.
Yeah.
Faster feedback.
No, behind you.
Oh, okay.
To see in real time.
What is that?
Yes, but
It's not gonna work.
Yeah.
Yeah.
I'm inclined 45 degree. Let's see. Yeah, it's already there. I'm now rotating. We using this angle. And now to other side. Yes, about 1 or 2
It's a little,
seconds.
it's a bit off, and it's also not using the magnetometer, so its accuracy is not 100%.
But do we see it's work fine?
Yeah.
Now keep it stable. Yeah. Now it's stable. I will rotate again.
Alan's toy.
Yeah.
Yeah,
It's playing around.
I could do it all the
All day.
afternoon. Very good.
All right, thank you.
Congratulations.
Thank you very much. Okay, then I think that's a successful presentation. And thank you very much.